We're good to go? We're good to go. Okay. Again, the slides are already up on my website for this presentation. And so what I want to do is just look at a few other bits and pieces in the Cgroups interface. 3 pieces, release notification, delegation, and thread mode, which is something of an innovation, or perhaps it's a dispute resolution in Cgroups version 2. That will become a bit clearer. Okay. All of these features, by the way, in some form were present in Cgroups version 1 as well, but the implementation or the design is better in Cgroups version 2, because Cgroups version 1, well, it was a mess. Okay, so what I mean by release notification, the general idea here is you've got a Cgroup, you put some processes into the Cgroup, but then eventually all those processes leave the Cgroup. Either they get moved into different Cgroups or they terminate and the Cgroup becomes empty. Now, in that circumstance, we might want a notification to tell us that the Cgroup has become empty, and we can get such a notification. This is what Cgroup release notification is about. And why might we be interested in knowing that sort of thing? Well, we might have a manager process that's created a number of workers and put them into a Cgroup, and when all of those workers finish their work and terminate and the Cgroup becomes empty, then the manager process knows the workers have done their work. Or we could want to do the thing that systemd does. Probably many of you are familiar with the idea that systemd has the facility to respawn daemons that accidentally terminate. Systemd is using this feature. It puts a process or puts a daemon process into a Cgroup, and it monitors that Cgroup to see if it becomes empty. And if it does become empty, then it knows the daemon prematurely terminated, and it restarts that daemon. Now, how does this feature work in Cgroups version 2? Inside each Cgroup, there is a file called cgroup.events, and this is a file of keys and corresponding values that have state information about the Cgroup. At the moment, there's only 2 keys. Once upon a time, there was only 1, but nowadays there are 2. And one of the keys is a key called populated, and it tells us, does this Cgroup or any of its descendant Cgroups have member processes? If the value in the file is 1, then somewhere in this subtree there is at least 1 process. If the key has the value 0, then this Cgroup and none of its descendants have member processes. And then the idea is that you can monitor these files to find out, these cgroup.events files, to find out when the keys change. And there's a couple of ways that you can do the monitoring of these files. One is you can use the iNotify mechanism, and which is a sort of a generalized file system notification mechanism. iNotify lets you do things like monitoring a directory to find out, was a new file created in that directory? Was a file modified in the directory? Was a file renamed? And so on. So we can use iNotify for this job, and if one of the keys changes, in particular if the populated key changes, then iNotify gives us a so-called modify event back, and then we can react to that event by looking inside the file to see, did the populated key change? Alternatively, we can open a file descriptor on one of these files and monitor that file descriptor using select, poll, or epoll, and if the content of the file changes, then what we get on the file descriptor is either a priority notification, if you're talking about poll or epoll, or what's called in select an exceptional notification. Once we've got one of those notifications, then we just go and parse the cgroup.events file to see what has happened to the populated key. And of course, it might not be the populated key that has changed. It could have been the frozen key, for example. So when you actually parse the file and check the value of the key to find out, has the populated key changed? You can have one process that monitors multiple cgroup.events files. Or different processes that monitor different cgroup.events files. The nice thing here is that this means you can have a different process monitoring different parts of the cgroup hierarchy, the cgroup.events files in different parts of the hierarchy, so that, for instance, one process might be monitoring all the cgroup.events files associated with a certain container. And another process might be monitoring the cgroup.events files associated with a different container, and so on. This was functionality that was not possible in Cgroups version 1. We talk about the notifications being delegated per container or per group of processes. Okay, so let's try this out. Give myself a super user shell, of course. And I'll make a child cgroup. Now, if I look inside that child cgroup, in fact, I'm going to do this a little bit differently. Now, I've got to remind myself of some syntax here, because I often get this wrong. Well, I'll do the simple thing first. Let's just cat, and I'm in the wrong place, of course, right now. Let's cat cgroup events. We see certain values there for the keys. There is no process inside this cgroup at the moment. Now, let's create a process, and in fact, no, before I do that, I'm going to use inotify_wait. inotify_wait is a command line interface to the inotify mechanism. And I'm going to say inotify_wait. I have to remind myself of the options there. I want to say yes, -q, -e, modify. And I want to do this repeatedly. And I'm going to say this on, I want to monitor this cgroup.events file. And whenever I get a notification, what happens, the form of inotify_wait that I'm using here, it's simply going to return, it's not going to print anything, it's simply going to return every time there is a notification event. So every time there's a modify event on that file. And I just go around in a loop calling inotify_wait again and again. The -q just says, be quiet. Don't actually give me any printed information, just return when there is a notification event. And whenever I do get that notification event, I'm just going to say, let's display the populated key in that cgroup.events file. And then I'm done. No, I'm not. What did I do wrong? Oh, yeah. Okay, good. Now I'm done. So now I'm going to create a sleep process. And then I'm going to move that sleep process into the cgroup. Now, when I did that, that generated an event because the populated key changed. And of course, the loop down below, when the notification occurred, my loop grepped for the key inside the cgroup.events file, and we said it's changed to the value 1. Now, let's create another sleep process and put its PID in there as well. It's a bit of a coincidence, exactly 100 apart. Okay, that didn't generate a notification, by the way. okay? Because the populated key is a Boolean key, telling us that there is at least one process in the hierarchy. Now, suppose I now say kill the first process, 348, 185. Again, there's no notification. The value of that key in that file, just cat that file. The value of the key is still 1. But if I kill the other sleep process, now I get a notification, okay? Because in that subtree now, there are no more live processes. So this is this idea of release notification. I think I've covered most of this. Yeah. Okay, so that's release notification. Then someone over here had a question that I said the answer is delegation. Was it? Yes, it was, yes. Everything I've been doing so far, I did as super user. Of course, that's not so nice if we're thinking about the notion of unprivileged containers. Containers run by unprivileged users, because we don't want to have the container need to be privileged in order to use cgroups. So this is what delegation is about: passing ownership of some sub-hierarchy in the version 2 hierarchy to some less privileged user. User ID 1000, for example. Need a bit of terminology: delegator and delegatee. What I mean by the delegator is the privileged user, probably super user, who owns the parent cgroup. And then the delegatee is the unprivileged user to which we're going to pass ownership of some subtree underneath that parent cgroup. Now, the way that you do delegation is just make the child cgroup writable by the delegatee. The usual way of doing that is to change the ownership of the directory, and then the directory is writable by the unprivileged user. So you change the ownership of the directory that is going to be the root of your new delegated subtree, and you have to change the ownership of some files inside that directory as well. The cgroup.procs file, so that the delegatee can write PIDs into that cgroup.procs file, and also the subtree control file, because then the delegatee can enable controllers inside the delegated tree. You might also need to change the ownership of a few other files, and the set of files whose ownership you need to change has evolved over time. There's been a few new files that have been added over time that they also need to be delegated. And then your question becomes, well, I'm using a certain kernel version. On that kernel version, when I do delegation, which files need to be changed? Which files need to have their ownership changed? Nowadays, the kernel has a little interface for allowing you to discover that information. There's a file called, or a pseudo file, syskernel cgroup delegate. And that file just lists the names of files that you need to change the ownership for during the delegation step. And so you see there cgroup.procs and cgroup.subtree control, but there's a couple of other files that might be present in the cgroup directory, and if they are, you also need to change their ownership as well. There are some files in the directory, though, whose ownership you don't want to change. And these are the resource controller interface files, things like PIDs.max and CPU.max, because they're being used from the level above to limit resources that come into this cgroup. And the delegatee, the less privileged user, shouldn't be able to change the limits that are coming in from outside the cgroup. So those files should still remain owned by the delegatee. So in terms of a picture, this is what the delegation step looks like. we've got the parent C group that's owned by the delegator, presumably super user. Then a child C group that we're going to delegate to the delegatee. So we change the ownership of that, that directory to being the delegatee. And then within that directory, we change the ownership of the other files that are shown here in blue, the ownership of those other files also to be the delegatee. But the other files inside that C group, the resource controller interface files, they remain owned by the delegator because they are what are being used to control from outside in terms of resources that come into this C group. Now, once we've done the delegation step, the delegatee, the less privileged user, can then create child C groups. Those child C groups will inherit their ownership from the parent C group, so they'll also be owned by the delegatee, and all of the files, including the resource controller interface files inside those child C groups, will be owned by the delegatee. So the delegatee can freely modify resource limits in the lower level C groups. Okay. Now, there's a set of rules which are called the Delegation Containment Rules. And the idea of the Delegation Containment Rules is that the delegatee is allowed to move processes around within the delegated subtree, but can't do things like moving a process from the outside of the hierarchy into the delegated subtree, or vice versa. And the rules go like this: that the writing process, which is presumably owned by the delegatee, in order to move a process from a source C group to a target C group, two rules. The writing process needs to have write permission on the cgroup.prox file in the target C group, and write permission on the cgroup.prox file in the common ancestor of the source C group and the target C group. Now, the effect of those rules is that, for example, the presumption here, well, there's various C groups here that are owned by different user IDs. The root C group, for example, owned by UID 0. But then there are other C groups that are owned by other users. They've been delegated. And the delegation containment rules would let us do things like saying we could move a user ID 1000 could move a process from C group M to C group N. The reason is UID 1000 has write permission on the cgroup.prox file in the target C group N, and also has write permission on the cgroup.prox file in the common ancestor, which is B. Likewise, UID 1000 could move a process from C group M to C group X. We need to have write permission on the target C group, which is X, and we need to have write permission on the cgroup.prox file in the common ancestor. The common ancestor of M and X is X. On the other hand, user ID 1000 couldn't move a process from C group X to C group Y, okay, because it doesn't have write permission on the cgroup.prox file in the common ancestor. And if you think about unprivileged containers owned by the same user, that feels good, because you wouldn't want to, a user could set up two different containers and then move a process from one container to the other. That would be icky. Okay, so let's try some things out. Maybe I'd just better start again here. Alrighty, so the top window here, I'm a privileged user, and just change my shell prompt to something less noisy. I'm going to create a child C group. I'll call it D group for delegated group. Now, if I do an ls-ld on that directory, okay, it's owned by superuser. But I want to delegate that directory to an unprivileged user. Okay, down below, I am user ID 1000, user MTK. So to do the delegation step, all I do as the delegator is say, change the ownership of that directory to unprivileged user and associated group on the group, but also on some files inside the group, cgroup.procs and cgroup.subtree control. Those are the only files. I happen to know this. What have I done? Oh, yeah. Hey, that's interesting, isn't it? Okay, let's undo that. Now, let's try and do that. There. I happen to know that those are the only files in that directory that need. Have I still messed up? Oh, yeah, thank you. You're all just here to help me debug. So, I happen to know that those are the only files inside that directory that need to be delegated. There is no file called Cgroup.threads in that directory, and there is no file associated with the memory controller either. Now, I can then do a bit of verification, where I say ls-ldn, long listing. In fact, we don't need the dn. Okay, those files have been changed to unprivileged owner, me, and I've got write permission on those files. Now, what that means, and I'll just down in the shell below, I'll just step into that directory. What that means is that as an unprivileged user, I could now create child C groups underneath that delegated C group. So if I say make the group 1, group 2, and then I do an ls-ld on those two directories, okay, they're owned by me. And if I look at the files inside one of those directories, all the files are owned by the unprivileged user. So this means that as the unprivileged user, I could do things like, once controllers are enabled, I could start setting limits inside those child C groups. Now, let's try to put this shell into that the delegated group. So I'll say echo $$ into D. Oh, I'm in that group already. Yes. So pwd echo $$ into cgroup.procs. Failed. Why is that? At a guess. I don't have write permission in the common ancestor. And you're quite right. There's one more piece that you need to add there, I think. Where does that shell live at the moment? At a guess. Which C group? Yeah, it's probably in the root C group. let's go and check that. Cat / proc / $$ / cgroup. Oh, okay, no, it's not in the root cgroup. It's in something that was created by systemd, of course. But the point is the common ancestor is the root cgroup, and I don't have write permission on the cgroup.procs file in the root cgroup, in the common ancestor. Okay, so to get the very first process into the delegated cgroup, that actually needs to be done by the delegator, the privileged user. So let's find out the PID of that shell. Okay, that's that PID. So then I could say here, echo that PID 3488550 into dgroup cgroup.procs. And then if I now grep, cat proc $$ cgroup, okay, the cgroup membership has changed. Now, I could, from the shell, because the shell is owned by user ID 1000, I could now create a process. If I look at that sleep process that I've just created, if I look at its cgroup membership, it's in the same cgroup as its parent, because that's how it happens by default. And what I could now do as the unprivileged user is say echo that PID into one of the child cgroup, cgroup.procs files. And that works. If I now again cat the proc.pid cgroup file, I see the membership has changed, and I could move it around a bit more, move it into the other cgroup, the other child cgroup, and again we see the path name has changed. What I couldn't do is something like try and echo that PID into sysfs cgroup.procs, try and move it into the root cgroup. This is delegation containment in action. I think I've covered all of that. Yeah, that's that. Okay, this is going to be a short session, but that means I can do a better demo of thread mode. Okay, so, or perhaps though, before I talk about thread mode, are there any questions so far? Because we have got a bit of time in hand. Or you can think of questions at the end. Yes, please. Are you talking about the rules? Yeah. Next one? Yes. Ah. Yes. Yeah, if you try to move from K to M, you're allowed to as user ID 1000. Yeah. I know it feels a bit strange because you've moved over a C group that was owned by a different user, but according to the rules, that's allowed. And perhaps if you'd like to think of it, from the point of view of, the tree root of X might be associated with a container owned by user ID 1000, and user ID 1000 is sort of God in that container. So you can do that sort of thing. But yeah, it does feel a bit strange. And this is a slightly unusual setup for you, but it's a theoretically possible setup. So what was, I thought you said, did you say J to X? Or K to M. It's K to M. Yes, that's fine. But yes, that's you couldn't move. That's true. According to the delegation containment rules, you couldn't move a process from J to K. Okay, it is a weird situation.
But then just keep going back. You move it from J to M and then from M to K.
Could you move it from J to... And I think according to the delegation containment rules, the answer is yes. Yes. It's a weird setup. But I'm pretty sure the answer is yes. I can't see any reason why not. I've never done that particular experiment. But yeah. Yeah, but I'm sure the answer is yes. Okay, thread mode. When Cgroups version 2 was initially designed, there was one of the design decisions was that the granularity for Cgroup membership will be at the process level. In other words, all the threads in a multi-threaded process must be in the same Cgroup. Version 1 had allowed something different. With version 1, you could have a multi-threaded process where some threads were in one Cgroup and other threads were in a different Cgroup. And for some controllers, this made sense. In particular for the CPU controller, people had use cases where you'd have a multi-threaded process where you wanted some threads that were subject to one CPU limit, but other threads that should be subjected to a different CPU limit. The reason that that idea was not initially implemented in Cgroups version 2 is for some other controllers, this made no sense. The most striking example is the memory controller. Suppose you had a multi-threaded process where you tried to put some threads in one memory Cgroup with a certain limit and other threads in a different Cgroup with different memory limits. Given that threads share an address space, what could that situation possibly mean? So when Cgroups version 2 was first implemented, the design decision was we won't have that sort of messiness. There'll just be thread level granularity process level granularity for Cgroup membership. But there were these use cases in version 1, especially to do with the CPU controller. And this led to a long-running skirmish between two different groups of kernel developers. And I said that Cgroups version 2 was released in 2016. The skirmish had already been going on for a year, and when Cgroups version 2 was released, there was no CPU controller. I don't know what the Cgroup version 2 maintainers hoped. Perhaps they hoped the problem would just go away and we'd get a CPU controller according to our idea. But the kernel scheduler maintainers had other ideas. So on the one hand, with the Cgroup version 2 maintainers that said the level of, for Cgroup membership, the granularity for Cgroup membership will be the process level. All threads must be in the same Cgroup. On the other hand, you had the kernel scheduler maintainers who said, if you want to merge a CPU controller into our scheduler, you're going to satisfy that use case that was possible in Cgroups version 1, where you could have different threads in different CPU Cgroups. One of the things that might not have helped here too much is that one of the kernel scheduler maintainers hates Cgroups. Wishes they'd never appeared. Anyway, eventually there was a compromise found, and this compromise was something called thread mode. And thread mode allows a limited form of thread level granularity for certain controllers, for the certain controllers where it makes sense. And how does this work? Well, now Cgroups have different types. We talk about domain Cgroups and threaded Cgroups. A domain Cgroup is one which has the original rule. A process in a domain Cgroup, all the threads must be in the same Cgroup. This was the original version 2 default. But what you can also do within this overall version 2 hierarchy is create what are called threaded subtrees. And in a threaded subtree, and you can have several different threaded subtrees, in a threaded subtree, you can have the threads of a process split across different Cgroups. There's one rule which is that all the threads in that process must be in the same threaded subtree. There can be many threaded subtrees, but all the threads of any particular multi-threaded process must be in the same threaded subtree. So there is now thread level granularity in version 2, but it's more restricted than version 1. And so we've got the idea like this. Here I've got a version 2 hierarchy where there is one threaded subtree. And there's a few threaded cgroups inside that subtree. And the idea is that you'd have a multi-threaded process where the threads were split across the cgroups inside that threaded subtree. Okay. Now, a change that happened at the same time is now controllers were split into two types, so-called threaded controllers and domain controllers. And the idea of the threaded controllers, these are the controllers that sensibly support the idea of thread level granularity for cgroup membership, where it's meaningful to split threads apart for the purposes of doing resource management. The other controllers, which is most of them, are the so-called domain controllers, and they only understand process granularity for cgroup membership. So these threaded controllers, they understand threaded subtrees. What I mean by they understand threaded subtrees is that, going back to that tree, sorry, I'll do the drawing here on the screen, that's a better idea, that going back to this picture here, for the threaded controllers, controller interface files, things like cpu.max, will appear in those child cgroups. On the other hand, for the domain controllers, the controller interface files won't appear because domain controllers don't understand threaded subtrees. For a domain controller, it looks like all the processes reside in the root of the tree, because domain controllers, they can't have their interface files enabled at lower levels in the tree. So the lowest level that a domain controller can do management is the root of the threaded subtree. Okay. Now, in order to do the management here of these cgroup, these threaded cgroups, there's a couple of new files that appear. There's now a file called cgroup.threads. If you write a thread ID into that file, that'll move a single thread into that cgroup. And this is the way that you split the threads of a multi-threaded process into different cgroups in the threaded subtree by using this file. And then there's another file, cgroup.type. And what this file does is expose or allow you to modify the type of a cgroup. Cgroups, to begin with, they have type domain. Domain cgroup only supports process level granularity for cgroup membership, but there are other types. There's a type called threaded, and this means this is a cgroup in one of these threaded subtrees. There are other strings that can appear in this file. Domain threaded. This means this is one of these, this is a cgroup that is at the root of a threaded subtree. It's at sort of that crossover point, going back here, it's at that crossover point between the domain outer world and the threaded subtree underneath. And there's one more cgroup type that I really don't want to get into. It's slightly confusing, called domain invalid. Maybe it's not so much it's confusing, I just don't buy the rationale for its existence. There is a rationale, but it's questionable, I would say. This domain invalid state, this is a cgroup that is invalid. Basically, it's a temporary state on the way to creating a threaded subtree. What you ultimately do with one of these domain invalid cgroups is turn it into a threaded cgroup. There are a couple of different ways for creating these threaded subtrees, and I don't have slides here to show you, but I'll just do the demonstration. You can find the details in the manual page. There are quite a few rules about doing this, and again, it's a bit more than I have space to cover, but I'll just do some demonstrations. And yes, after that we're done. Now, what I'm going to do is make a little bit of sub-hierarchy and then make a threaded subtree. So I'll make a director under here, in fact, I'll say make -p, so A, B, C, D, and maybe C and E, and maybe A/X/Y /Z. I think that's enough. Now, one way of making a threaded subtree is I write the string threaded into a cgroup.type file. So I'm going to write that string into the cgroup.type file of the cgroup C. Now, what this does is make that, let's cat that file just to verify the change. And I should have catted that file beforehand, but if I can just cat another file just to demonstrate. The default, that was not the file I meant to cat. Let's look at the cgroup A. That's the default type for cgroups. Now I made C threaded, and what that did was cause the parent of C to become domain threaded. This is a slightly weird way to go, but it's how it works. This caused the parent C group to become domain threaded, and all the other descendants of the parent C group became invalid. So if I then said cat A/B/D/cgroup dot A/B/D cgroup. Why am I getting this wrong? Oh, yes. A/B/D/cgroup.type. The other descendants underneath B became domain invalid. Now, if you're trying to do these experiments, you quickly start to go a little bit mad, catting files, trying to visualize things, and it's not that much fun. So you want a little Go program that I prepared earlier. And so I can now say go run oops, of course I should have said mtk view v2 cgroups, and I want to view the hierarchy .go A/B. And this program gives me a little visualization, because that's much easier than catting files all over the place. And so what we can see is that C has type threaded, the parent has type domain threaded, and the other descendants of the parent have become invalid. If I'd done the viewing instead at cgroup A, A has type domain, underneath B has domain threaded. Now, the next thing I would do to create a threaded subtree is I've got to turn all those domain invalid cgroups into threaded cgroups. And so I say echo threaded into A/B/C/D/cgroup.type, and the same thing in the cgroup E. And then if I revisualize, now I've got a fully threaded subtree. What I could now do is put a process inside that tree. Now let's make a process What this program does is create one thread for each command line argument, and each of the threads tries to burn some CPU time. So, and 3 threads is enough. Okay. Each of those 3 threads is getting 100% of CPU time because, of course, I've got a lot of CPUs. And what I could then do is move that process into the threaded subtree. And the way that I do that is I say echo the PID, which is 351162, into A/B/C cgroup.procs. Now, if I cat that file, something slightly odd happens. I get an error. The reason is that from the perspective of the threaded subtree, the process is considered to be a member of the root of the threaded subtree. In other words, it's considered to be a member of A/B, which was the root of the threaded subtree. So processes are always considered to be members of the root of a threaded subtree, but individual threads can be members of various cgroups within the threaded subtree. So for instance, if I said cat A/B/C/cgroup.threads, there's all the thread IDs. They are in that descendant cgroup. Again, you go a little bit mad trying to cat everything here. And again, my little Go program just makes life a little bit easier by showing me where the PIDs are and where the thread IDs are. All the program there is doing there is inspecting cgroup.proc files and cgroup.threads files and displaying the information. Now, what I could then do is things like this, where I say echo let's say 20,000, 100,000 into A/B/C/D /CP. Oh, hang on, I've got a little problem there. I was going to enable CPU limits, but of course what I haven't done is enable the CPU controller all the way down at the into various C groups. So let's just quickly do a little bit of, first of all, enable CPU in the Subtree control file at the root C group, then in A and B and C. I really like my little Go program because it gives me visualizations of all these things, which would otherwise I would go crazy, because it's telling me the CPU control is enabled now in those C groups. So then I want to do things like saying echo some quota and period into A/B/C/D/CPU.max. Just by the by, little test, I enabled the CPU controller in A and B and C, but I set a limit in D. Why didn't I need to enable the controller in D? No. Martin. It's always the level above that it's controlling the next level down. If I want to do control in D, I have to enable the controller at the level above. Okay, I've set a certain CPU limit there, and let's set one in E as well. And then I could start moving threads into these C groups. So I could then say echo, say 351162 into A/B/C/D/cgroup.threads. And of course, I meant to use a different number here. Let's make the limit in E 20%. And what you can see down below, by the way, if I just freeze the output there for a moment, you can see there that this thread is only getting 50% of the CPU now. 50% of a CPU. And I've set a different limit in Cgroup E, so let's move a different thread in there. 6.3. And again, we can see there it's converging on a lower value now. Oh, I measured into the wrong C group, didn't I? I meant to move it into E. Okay. Okay, we're at steady state there now. You can see that this thread is getting 20%. This thread is getting 50% of a CPU. The other thread is getting 100% of a CPU because it's not limited by anything at the moment. Okay. Now, if I put two threads into the same C group, let's put the third thread also into C group E. So if I put, just resume that output. If I put 351.664 into E as well, give it a moment. It's going to take me 10 seconds or so for it to stabilize now. Okay, what you can see that the two threads that are in C group E are sharing the 20% that is available to that C group. And so they're each getting 10% of the CPU. Okay, that is essentially thread mode. I think I'm done, and there's a few minutes left in case there are some questions. Martin.
The pick C group in a threaded model, how does that work? Is it stopping a thread from forking too much? Or
Okay, so nice question. The PID's controller is misnamed. The PID's controller, it's not limiting PIDs, it's limiting tasks, it's limiting threads. Individual threads count against the limit. So if you took a multi-threaded process and put some threads in one PID C group and other threads in another PID C group, then it would limit the ability of each of those threads to create further threads or further processes. That's why it's a threaded controller, despite the name. Other questions? Yes, Joachim.
So the domain invalid was just like a placeholder for
There is a story. Look, I am just the messenger, okay? To me, the question is, why do we need the domain invalid mode at all? Why couldn't you just write domain threaded into a certain C group and that makes everything underneath threaded? That would be so much simpler, wouldn't it? Yeah. But it's not the world we have. And this is because at a certain point there was a discussion that there might be possibility for something called mixed mode, where you might have a threaded subtree, but then underneath there might be some domain subtree. Now, what this could mean was never fully elaborated. But then the decision was made, well, let's allow for this in the future. We don't know quite what it's going to look like, but we're going to allow for it. And what this means is that we don't necessarily want to make the decision up front what should be the type of one of these C groups underneath the threaded subtree. I don't buy it, because if we need to do that thing differently, then perhaps we could have had a world where you just wrote domain threaded into a cgroup.type file, and it did, made everything threaded underneath. And if you need to do something else different in the future, you wrote some different string into these files. But it's what we have.
there's no like situation that causes Cgroup to become domain invalid except for what you mentioned.
That's right. Yeah. Please, question. No. So underneath the domain threaded C group, the only kinds of C groups you will find are either threaded or domain invalid. Yeah.
So if you wrote threaded to C group, that makes the parent the domain threaded, and then you also make all the other ones like siblings invalid.
Yeah. So if you write threaded into a cgroup.type file, that makes the parent domain threaded, and everything underneath that domain threaded ancestor domain invalid. Everything else, domain invalid. It's weird, but it's the way it works. No, the only string you can write to these files is the string threaded. In other words, the only explicit transition that you can make is to convert a cgroup to type threaded. Now, there are implicit transitions that can happen, though. And I'll just quickly illustrate that. Let's do that visualization again. The cgroup there, X, has type domain. And so what if I make the type of Y threaded? So I'll say echo threaded into a/x/y/cgroup.type and visualize. Parents become domain threaded. The sibling has become domain invalid. But what if I do this? rmdir a/x/y. Now the reason that X is threaded, domain threaded I should say, is because it has a threaded child. What if I remove that threaded child? I can do it, and then what happened to X? It reverted to type domain, and its child reverted to type domain as well. So there are these kinds of implicit transitions that can happen if the ancestor is no longer forced to being domain threaded. There is another way that you can create a threaded subtree, but I won't try and talk about that here. But basically, there's two ways you can create a threaded subtree. But if the thing that triggers the creation of the threaded subtree is undone, then the ancestor, the domain threaded root, reverts to being type domain. In this scenario, yes, but in the other scenario, it looks a little bit different. But even so, if you reverse the steps, then the conversion to domain thread is undone. Joachim.
I'm just curious about one kind of weird situation, which is possibly not good if you're in that situation. But let's say you have a main threaded cgroup.
Yes.
And then
Sorry, if you have domain threaded cgroup, could you? Yes, you could. So let's say make. So well, here's our visualization at the moment. We've got A and X and Z. Let's make Z threaded into a/x/z/cgroup.type. Now that, of course, turned X into domain threaded. Now what if we then wrote threaded into a/x? That's what you're talking about, isn't it? Yeah. Hang on, now I'm confused. Oh no, I think that's because of something else that's going on, which is I've got domain controllers enabled at certain levels above. Yeah, so you can actually do this sort of thing, and if I didn't have other domain controllers enabled, because there are some rules that I haven't talked about, but you can do that sort of thing where you write threaded into a cgroup that is currently domain threaded, and that causes the parent to become a domain threaded, and that domain threaded child becomes threaded now, and the other descendants become domain invalid. Yeah.
So in that case, the sibling in this case is also domain threaded and has would that be
No, if a cgroup, if a sibling is already threaded, that stays threaded.
well, but this sibling is domain threaded. So what happens to the domain? Is that what stops this from?
No, I think it should become threaded as well. Yeah. There's something else that's to do with the controllers, I think, and I'd have to just look more closely. I've broken another rule that I haven't explained. Yes, please. Oh, that's the rule I've broken. Thank you. I've just realized it. That you, if I do the visualization, thank you for that question. The rule that I've broken is you can't turn a particular node into domain threaded if there are descendant cgroups that have member processes already. And I was trying to turn A into domain threaded, but already underneath A, there is cgroup B that has a member process. That's the rule I broke. I wasn't thinking quite quickly enough. But, you know, to finally do your question, Joachim, in a different way, let's just say make the P/Q/R. Make the -P. And then do the visualization on P. Okay, and then if I make echo threaded into P/Q/R/cgroup.type, do the visualization, the parents become domain threaded. But then if I do that on Q and visualize again, that's turned the Other questions? I think we're at about time. Okay, thank you for your time.